Hello, everyone, and thank you for attending today's webinar, A Path to Productivity, EDS Application Solutions. Before we begin, I would like to cover a few housekeeping items. At the bottom of your audience console are several applications widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you will receive an answer later via email. We do capture all questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click the help widget. It has a question mark icon and covers common technical issues. An on-demand version of this webcast will be available in approximately 1 day after the webcast and can be accessed during the same audience link that was sent to you earlier. My name is Tara Niles, and I'm the EDAX Global Applications Manager here at EDAX. I'd like to thank you for joining on for this exciting webinar. So for those of you who have attended our previous webinars, thank you for continuing on. And I'd like to take just a moment to recap one of our previous ones, which was a quantitative analysis webinar. And in that webinar, we talked about how to obtain the highest quality quantitative analyses for your EDS analysis. And during that, we talked about how important it was to keep in mind all of the quantitative considerations, things like matrix corrections and overvoltage factors, things that help make the algorithms run more effectively. We even talked about things like ionization potential and how to make sure you can maximize the quality of your data. In this webinar, though, we're going to take it to a different approach. This webinar talks about productivity and specifically how we can use advancements in the latest silicon drift detectors and software programming to really break the rules. And these are breaking the traditional rules of thumb and standard practices that many of us longtime microanalysts have been doing for many, many years. These days, with the latest advancements, we're actually able to change the whole paradigm of how we can do microanalysis, yet still without sacrificing quality. And so if you were lucky enough to go to this year's Microscopy and Microanalysis Conference or at the European Microscopy Conference, you may have seen the latest technologies and seen a couple of buzzwords, things that emphasize getting things done quicker, faster, and easier. So how the technologies help make our jobs more efficient, how our detector collection efficiency impacts our analyses. Also, how we could increase productivity by speeding up the analyses and the collection times or getting maps done more quickly. And finally, you may see some high-speed EBSD cameras, high-speed data collection, high-speed mapping. These are all important, but you might be saying, hey, Tara, I'm a scientist, and my goal is to ensure that I have the highest level of quality. I'm doing a lot of work that where I have to report results that solve some very important problems for my company. Or I'm doing some very important research where I want to make sure that my quality of data is first and foremost the driving force. And I am keeping that in mind when I go through this webinar. And that's why each time that I propose a change in a rule of thumb, that I'm also backing it with data that backs up how you can still ensure the quality of your data even while you're pushing latest acquisition speeds to increase your productivity. And whether we're in industry or academia, university, government, wherever it might be, we are scientists, but still we have an over-present need to get data reported into other people, to our managers, or in some cases to our professors or to our research grants. So there is always the time component. And for this webinar, our goal is to make sure that we pay attention to the quality when we're now addressing common EDS collection considerations. And so this webinar was designed for maximum productivity, and we shortened the length of time so that you could come in and get some new tips and tricks and then go about doing your work very quickly. what I'll be doing is introducing some new changes to common collection considerations, but also using data and examples to back up these new points. At the same time, I'm addressing some of the new applications in microscopy and microanalysis that I've been seeing trends in the marketplace these days. That's quite interesting, some places that we're going. And also for you tried and true microscopists and microanalysts, we have some new approaches to traditional analyses. So even if you've been doing the work for many, many years, we can propose some new approaches. One of the activities that we do in applications very frequently is work with customers for training. And one of the most common questions that I get when I work with customers on training is, how long should I collect my data for? In the previous webinar, we talked about how long we should collect our map data for to ensure the quality. And here I'm going to take a little bit different approach and focus on the spectrum itself. So when I first started working here at EDAX about 20 years ago, the old rule of thumb was collect for 100 live seconds, and that was a time-driven approach. And that's pretty much the practice that I've stuck through to for many years. When we take a time-driven approach, we have to say an amount of collection time. But then we also need to consider other factors, supporting conditions that back up that amount of time. And those are things like count rate. So for example, when I said 100 live seconds, I was working at about 1,000 or 2,000 counts per second when I first started with SILI detectors. But then you also have to think about dead time, because of course there's time spent on electronics processing. And the dead time actually reduces the amount of live collection time or time going into your data. So in a time-driven approach, nowadays with silicon drift detectors, we collect much more quickly, but we still say something like, well, I would suggest you collect for 20 clock seconds, and that's when your count rate is about 10,000 counts per second, and you have about 10% dead time percent. And that means that it's really not just quoting the amount of time, but it's quoting the amount of time and other supporting conditions to make sure that all factors are considered. But now I'm proposing that we take a more data-driven approach. And this is actually something that one of my colleagues, Pat, and I have talked about for a while. And in fact, if you go to our website, you can find some of our materials on data-driven approaches. In fact, we have a termination criteria for map collection, which is very similar. What this means is that we collect our data for a certain until a certain number of counts is achieved. We're not quoting a collection time per se, but we're saying, well, collect until you reach 100,000 counts per second. Oh, I'm sorry, until you achieve 100,000 total counts in your spectrum. And so about 100,000 total counts would be a good goal for qualitative and quantitative analysis when you have major elements. And in my experience, if you have minor elements, you might want to collect until you have about 200,000 total counts in your spectrum when you're doing quantitative analysis with minor elements. And if you have trace elements present in your sample and you want to do a collection detection of those trace elements, this is where you have maybe less than 1% of an element in your sample, you might want to collect for 300,000, 500,000 total collection in your spectrum, maybe even longer if you're doing quantitative analysis, because of course the error is going to decrease the longer that you collect for, the more counts you have in your spectrum. And when we do a data-driven approach, we then have the ability to have flexibility with what our conditions are. And so to get to 100,000 total counts in our spectrum, we could work at 10,000 counts per second with 10 clock seconds with additional time for dead time. And what 10 clock seconds really means when you consider dead time added to it is 10 live seconds. So the live collection time that EDAX has in our software allows you to make up for the time lost to dead time. And of course, we don't want to lose time to dead time. We want to increase our productivity, and that's where the latest technology changes are taking us. And we'll see some more examples of that in the next few slides. The other way we can get to our total goal is by, say, working at 100,000 counts per second for one live second. all modern-day microscopes have the ability to achieve nice high beam currents. Many mainstream models can work in the 2 to 5 nanoamp beam current very easily. Only occasionally will you even need to go to 10 nanoamps beam current to get to those higher count rates, depending upon what your beam voltage and sample conditions are. But there's really no challenge in achieving these higher count rates these days with the latest microscope technologies as well. And so for those experienced microanalysts out there who are looking at this, you might be saying, well, I know that there is actually something changing between those 10,000 counts per second and 100,000 counts per second. And that's the concept of amp time and dead time. And so we are, in fact, speeding up our processor in order to be able to work at 100,000 counts per second. And what I'll explain momentarily is how we could now do that with the latest silicon drift detector technology with very little trade-off. Before we go into an example, I'd like to show some of the ways that we're implementing this into our software. So now with a data-driven approach, we take the total data quality into consideration, and we allow you as the user to work in quick, standard, or high mode. So specifically, say for mapping, if you want to collect until you have a certain number of X-ray counts per pixel in your map set, you could select one of the preset modes. You could also change your own mode or even work in manual conditions and fully control all of your collection conditions. And I'm going to turn us over to uphold now for just a quick second to get an idea of where you as the user, microanalysts out there, how you're currently using your EDS systems. How long do you typically collect your spectrum for when you're doing a qualitative or quantitative analysis? And if you would, just take a moment to select one of the radio buttons for them. And I'd like to see kind of a good get a good idea of where the typical user is these days, how long collection time is for you guys. And we put the first few options as time-driven, and the last option is total counts-driven. So there might be some of you out there who are already more progressive and going with total counts as your ultimate goal. And I'll just give another moment or two so that you can select your typical spectrum collection time. And this kind of information is, of course, always used by us as we go into our approach as well. We try to do our analyses as similar and as representative to the real-world microscopist user needs as we can. So I appreciate your input. Of course, click on the Submit button on the lower right-hand side when you're done. And I'll move along. Okay, so we see a lot of people collecting for 50 to 100 seconds. Over 50% of you are collecting for a good amount of time, a lengthy amount of time. And that does go hand in hand with the traditional microanalysis approach, especially for SILI detectors. And so certainly there are probably some SILI detector users out there. Probably the quicker collection, the 30% that we have for the 20 to 50 seconds, those are probably some of our silicon drift detector users. And only a small fraction of you working in the 1 to 19 seconds. I do applaud you guys who are. I imagine that you're probably pushing your beam currents and making the most out of your microscope. And it's also really nice to see that there is a good amount, 10% of people are total counts driven. So already the industry is changing a bit towards that total goal of data driven. Okay, so in this example, I'd like to show the difference between 100,000 total counts when we collect for 10 seconds at 10,000 counts per second. And the first collection condition is the lower count rate, the 10,000 CPS. This is, of course, a metal alloy, and it can very easily achieve 10,000 or 100,000 counts per second or more at 20 kV. And when I toggle into the 100,000 counts per second, there's very little change to this spectrum. So we could see that the scale is about the same, the spectral appearance looks about the same, and they both have our major element peaks there. And of course, the real important thing is not how the spectrum looks, but what we do with the counts and how accurate is the data that we're getting. Are we sacrificing anything as we change to the higher count rate and the 1 second collection condition? And so the first area that I'd like for you to focus on is the column for weight percent. And you can see that there's very, very little difference between weight percent from the first collection condition, which is 10 seconds at 10,000 counts per second, and very similar result in weight percent for the 1 second collection at 100,000 counts per second. Very, very similar results. We're not sacrificing anything by speeding it up and collecting 10 times quicker. The next thing that I'd like to bring to attention is the resolution of the detector. And this is where I said for those experienced microanalysts out there, you might notice that for sure something is going to change if I'm ramping up my count rate, and that is our detector resolution. And we could see that we go from 128 EV to 131 EV. A typical detector spec is somewhere around 129 or 130 EV, and for sure the 128 falls within that range. But you can see by speeding things up 10 times quicker, we only lose 3 EV in resolution, and we lose no accuracy as far as weight percent is concerned. So the next question that I'm going to address is another common question during the EDAX training process, and that's what dead time to use. So dead time is a factor that considers the detector efficiency of conversion from input count rate to output count rate. That means that the input count rate is the raw counts that are hitting the detector. The output counts are how many are making their way through the electronics processor and making their way into the spectrum. Dead time, quite simply, is lost time. And in a productivity webinar, we want to minimize the amount of time that we're losing. So the historical rules of thumb for those silicon and lithium detector users out there, you're probably working somewhere around 20 to 40% dead time. And that's what we would instruct our analysts to use during our training classes. We would usually say about 20 to 40% for a SILI detector. When we moved into SDDs becoming mainstream, we actually sped that up. And I remember having this discussion with my European colleagues as well and saying things really are changing with the silicon drift detector because it's much faster and does a much better job of detector efficiency. We could actually work faster without losing too much time to dead time. So that's when we changed to propose that a typical target range for dead time would be 10 to 30%. And here in today's webinar is where I'm going to propose that with the latest silicon drift detector technology plus cube electronics, which are available in the latest EDAX Elite, Octane Elite detector series, we can completely change this paradigm. And here's where I'm saying that a target dead time to use of less than 10% will provide maximum productivity with minimal trade-off. We always want to work close to 100%, whether it's for our fuel efficiencies in our car or even our grades in school. The 100% is a target. So here in this case, we want to minimize the movement away from 100%. We want to maximize the productivity and work at the smallest dead time possible. So now I'll turn it over to another poll and ask you, as a typical microanalyst, what is your typical dead time target range? And again, please remember to click on the Submit button at the lower right-hand side. And of course, this is likely detector dependent as well. With the SILI detectors, there is a good reason to work at the 20 to 40%. And as we sped up to the SDDs, good reason to work in the 10 to 30. And if there are any brand new EDAX detector users out there, you probably may have already discovered just how quickly and efficiently your detector can work, and you might be working at that 10% or less. Excellent. Okay. So this represents a good cross-section. I would imagine that most of you out there are using the silicon drift detectors that have been out there for the last 8 or so years. And it's nice to see that there are a few people who are speeding things up, working at better than 10% dead time. Those are probably the latest detector technology users and making sure you're increasing your productivity. Certainly the 20 to 40% dead time is workable for those users still using the silly detectors. And thank you for your poll results. That's helpful to us. So the reason why silly detectors would work in the 20 to 40% range was because you had very little flexibility as far as amp time processing goes. Typically there were only 2, maybe 3 different amp times, and so you had to make a choice between throughput and resolution. The throughput for silly detectors really stayed within the about maybe 10,000 counts per second or so range, and not a whole lot of ability to get a lot of counts output. Also, at the same time, the resolution dropped precipitously, very quickly. And so the slower amp time would have a nice res of about 130 EV, but when you went to the faster amp time, it could quickly drop to about 180 EV. With the SDD detectors, we've now pushed things towards the 10 to 30% dead time range, and that's because we have faster electronics. Those faster electronics allow us to get throughput in even the 500,000 plus counts per second range. When we do this, though, with the previous generation of detector electronics, we would often work at the 130 EV range, maybe sometimes in the 140 EV range as we got up to 100 or 200,000 counts per second. But if we were really pushing the max output, we would be over 200 EV. It is a lesser focused on spec, but it is out there. So that's always a good question to ask. What is your resolution at your fastest processing time as you're looking at your detectors? Also keep in mind that there are various artifacts. There's pile-up peaks within the spectrum, and then there's also the loss of the low energy even at the fastest process time. So that was something that we would have to suffer through with the earlier versions of silicon drift detectors. And here's where I'm proposing a new standard where better than 10% or lower than 10% dead time will give you the maximum productivity. And when we say minimal trade-off, the latest detector technology allows us to work with a resolution range better than 160 EV or lower than 160 EV. So even at your fastest processing times, at your maximum output counts per second, you're going to be still retaining a really high quality in detector resolution. And now I'd like to show an example of how decreased dead time leads to increased productivity. And I'm using just a moderate collection condition example, so working at 20,000 counts per second input. And at a typical dead time, what we would propose is a previously typical dead time of 30%, that would give us 15,000 output counts per second. So 20,000 in, 15,000 out with 30% dead time. And if we're collecting for 5 live seconds, that would mean that it takes us about 6.5 clock seconds to get there. So we have about 30% more time devoted to our collection because we're making up for that amount of time that's lost. And so since most of you are collecting in the 50 or 100 total seconds collection range, this would translate even further. 30% longer time for 100 seconds makes a significant impact. And this particular spectrum has 130.9 EV resolution at that condition. And the next example that we're comparing to now has a dead time below the 10% at 4% dead time. So we have 20,000 counts per second in, and we've got about 20,000 counts per second out. Only a real little bit of counts are actually lost. And that means our 5 live seconds collection time is actually 5 clock seconds. So we're not collecting for a longer amount of time to make up for the time lost in dead time. And all we've sacrificed is just a few EV in resolution because now we're 133.3 EV resolution. And so The conclusion here is we have the same amount of total data in the spectrum, but we're collecting 25% faster, and we only sacrifice 2.5 EV of resolution, and that is a very, very small amount of quality to lose when we're going that much faster. Now we'll use a more extreme example where decreased dead time shows increased productivity. And this is an example where we're running at really high counts per second throughput and very, very quick collection time for a particle analysis. In this case, we have 1/10 of a second collection time. One spectrum for each particle is being collected out of our 60,000 particles in an automated overnight run. So this is where the computer is doing everything for us, but what it means is we could get volumes and volumes of data in a multi-field analysis for a mineralogical sample. And we could see that our error percent is very low. We're shooting for a specific known compound, and we have a really nice error percentage, even in that extremely quick collection time for many, many particles. So the effect is cumulative. It compounds over time. And now I'll shift into some new applications, specifically that we're seeing the last year or two in microscopy and microanalysis. We've seen more of the entry-level SEMs, which are actually growing the market and the ways in which microscopy and microanalysis is used. And that inevitably grows the market in new directions. It means that new types of people are using the systems, and people are finding new ways of using the systems. We see an increase in quality control, production line level work, and also technician level, entry level analysts. Also really encouraging is that we're seeing use of microscopy and microanalysis in primary schools, so younger students than ever who are gaining access to these tools. Also, government and regulated industry is better able to do their screening work more quickly and effectively with some of these tools. And the first example shows how we ensure quality. So many companies do failure analysis or quality control. And this example here is one example of quality control. And it's quite an interesting example. So I wonder if anybody has a guess of what we might be looking at. You might notice the droplet appearance may be some type of oil or contaminant. And I'm going to zoom out to a lower mag, and maybe now it becomes more apparent what we're looking at. This is, in fact, a customer repair unit, EDS detector. So here at EDAX, we strive for the maximum quality to support our customers in their detectors. So when we get a customer repair unit in, our factory and repair guys are taking a look at your detectors with optical microscopy, and even sometimes we use them in the SEM to evaluate what's going on. And in this case, you could, at low mag, you could see the bar arrangement for the detector window. And fortunately here, we're just looking at some oil contamination on the front of the detector that hasn't completely failed the detector. There's not a hole in it. So the good news here is something like this can be cleaned. The bad news is you want to avoid contaminating your detector, of course, because that will eventually break it down. But with the latest silicon nitride windows, you can safely plasma clean your detectors, and so something like this would be avoided. You'd prevent an EDAX repair altogether. But here at EDAX, we do now strive to ensure the quality of all detector units that are out there, and using our own microscopy and microanalysis equipment to ensure that quality. And the next range of work is screening for unexpected or unintended materials. This is something like materials verification. So maybe raw materials, supplied parts, something that's coming in from a supplier that a producer is going to evaluate to make sure it's the proper material. Or also for some of these screenings, looking for unintended materials or undesired or controlled materials in goods. So these could range from applications anywhere from food, FDA looking at packaged foods, looking at food inside of a package still. Jewelry, monitoring, making sure that the expected material is there, or even a few years ago I remember seeing a thing about cadmium in some vendors' jewelry coming from overseas, so we want to make sure that that's not in there. even animal feed, making sure that there's not materials in there that we don't expect, electronics, counterfeit goods, fertilizers, auto components, really everything that we could think of. Now that we're looking at production line and quality control environment, we can see it all and really grow the range. So in this example, we're looking at a, quote, silver ring. So this was something that was expected to be a silver ring. We could see that it's quite dirty, but for those microanalysts out there, we're looking at the latest software that we have, the EDAX APEX software, and very quickly in your spectrum, if you're experienced, you might see this series of peaks and notice that, oh, okay, yep, that looks like my silver. That looks like what I'm expecting just by looking at the spectrum alone. But for those of you who are more entry-level users who are using EDS for the first time, looking at the spectrum peak probably isn't doing you a whole lot of good. So what we do in the APEX software is simultaneously in live time report the quantitative results. And if you can see here that sure, silver is in fact present in the material. And we even give you graphs that show how much silver quantitatively is present in the material. So we have 44% silver within this field of view, this collection area that we're looking at. And this was done in just a quick collection time. And the next one that we look at is another piece of jewelry. And we see that we have gold, which is probably good news for whoever purchased this. But then there's also a peak here when we look at the gemstone area. So the ring itself has some gold on tin, but there's something else that comes into the spectrum when we look at the gemstone area. And that's the peak that we see, the small peak right there in the center of the spectrum. And this is where we're ensuring the data quality by making sure that you do an accurate identification of your elements present. So it's an unknown peak, and I'm going through a manual ID procedure. And if we identify that peak as sulfur, so the small symbol there is sulfur, hopefully you can see that. So in the center of the sulfur peak, that light blue outline is the model of if this was sulfur, what would it look like? And so if you make an inaccurate identification, our deconvolution line will catch you and alert you to say, hey, that isn't sulfur, that's something else, something is going on there. And now I'm going to zoom in a little bit more, and we show the label with lead. So if we identify that peak as lead, sure enough, that light blue line fits perfectly with the acquired peak, and we confirm that that is, in fact, lead in the ring. Definitely unexpected or unintended, undesired material. The next thing that we're going to show is how we can make the software tools useful for routine users. And so these can be some experienced microanalysts who do the same thing over and over. In fact, this was a request a few years ago from one of our customers in the aerospace industry. They commonly collect a certain size box over and over again, and we do take that input and we do incorporate it into our latest generation of latest generation of software. And so now this ability to define certain areas and then use a stage table and have each of those different areas outlined with their own collection conditions. We can save that collection table and use over and over again for different areas on the same sample or even for different samples. So once you define your recipe or your collection recipe area, you can simply save it as the APEX multi-fields data table and use it over and over again. So for those of you doing a lot of the same qualification or verification, your life suddenly got easier with having to be able to use this stage tool all the time. And another example is in the pharmaceutical arena, which is an area that we're seeing really good growth for in the quality control line. So screening for visual defects is not too uncommon. And so if were to have a screening line where you're visually inspecting them, if you see something that looks different, then you could easily put it into, in this case, this came off of our tabletop SEM here at EDAX, and we're able to get an image pretty quickly. We confirm the defect area. It looks irregular in the coding over here. But when we do a spectral analysis, we don't see anything chemically different. All of the chemistry collection between the unusually looking area compared to the other areas is about the same. Even the map confirms that there's not too much chemically different going on. We don't see any new element or different element jump up in that area. But what we do see is in our CPS map, our counts per second map, we actually see a dip in the count rate. So our CPS map is shown here in the upper right, and in the electron image, we don't see any dip in the center. It's just, it visually looked a little bit different. But now in our CPS map, we actually see that we have a recessed or a divot or an opening in the top of the material. And in fact, there even is a crack that we see here, and that is highlighted by our CPS maps. So the CPS map is a useful tool that reveals changes in topography that might impact your analysis. It might be a visual defect, or it might change the appearance in the chemistry, because of course it looks like we have a loss of oxygen and carbon in that area as well. So the conclusion here, and here's a zoom in showing how useful CPS maps are to reveal that change in topography. So the conclusion is that this one doesn't have any chemistry differences. It's a morphological defect only, and not any changes in chemistry, nothing to worry about on the quality control line, just simply maybe a little dip in the sample or a dent in the sample. So with this, we come to the conclusion of today's webinar on increasing productivity. And now we can go back to work. I'd like to encourage you to ask any questions, and if you have anything, please submit the questions via your Q&A widget at the bottom. Just simply type them in. And the first question is a very interesting one. We've got a team user. Nice to see. Thank you for using the EDAX team software. And if you're a beginner with SEM EDS, as you mentioned, the APEX software might be something that you'd like to explore. So certainly reach out to us. We've got your email address, and we could start some communications about the APEX software. And that will streamline your analysis. APEX is geared towards the entry-level users, people just starting out in EDS and microscopy and microanalysis. So certainly, let's set up a time to discuss APEX. Another one is, I almost never see an escape peak with STD. Can you explain? So there are probably a few reasons for that. So first one is silicon drift detectors do still have the potential to have an escape peak. And that escape peak would be an artifact peak where an incoming X-ray displaces a silicon atom, creates a silicon X-ray, and reduces the incoming X-ray by the amount of energy of silicon, or 1.74. So if you're not seeing the escape peak with your SDD, that's good news. It means that you're probably using our escape peak correction. And that is the ability to detect the escape peaks, which happen with a known percentage amount. And so it looks like your detector and software are correcting the escape peaks for you. Very good question. Hi, Joe. Most EDS manufacturers report quant data to 0.1%. What is a realistic level of accuracy that we can expect from a typical EDS with SDD? Very, very good question. So yes, the 0.1% is a good rule of thumb for all elements about sodium and above. As you know, the sodium and below is a little bit more challenging because of the low energy of the X-ray and the high amount of absorption. So the changes with silicon drift detector The silicon drift detector doesn't have a direct impact on your sensitivity level, but what it does have a direct impact on is the amount of statistics that you can achieve. And of course, the increase in statistics means a better assurance of the quality of the detection. So everything in the world of analytical chemistry is signal to noise, no different with the EDS detector technology. We're going for the more signal to noise that you have, the better that your detection, mean detection limits is going to be, the better that your mean detection limits will be, and the better that your quantitative analysis will be. I said an error there. You had actually mentioned 0.01%. I answered the question as 0.01%, but I believe I read it as 0.1%. So it is true that about 0.01% is the target that we would say as a minimum detection limit. With silicon drift detectors, you'll achieve more statistics more quickly, and so your error percentage will be reduced for that mean detection limit and also for your mean analyzable limit. How often do we need to do an energy calibration? That's a very good question. With SILI detectors, changes in the environmental conditions, the temperature of your room, maybe some electronics interference, that used to mean that energy calibration for a SILI detector was advised every month or so. With the silicon drift detectors, we're actually much more stable, and the ability to correct for the small changes. And so we'll typically say if you're in a regulated industry, you might want to calibrate every 2 to 4 weeks, but many users go for 1 to 3 months or even longer without calibrating. In fact, it's not unusual or unheard of to not calibrate at all with a silicon drift detector and just save that for your service engineer. And one of the questions is, do you have concurrent EBIC for scan analyses? At this point in time, we don't have concurrent. It can be done with different tools integrated into the same microscope, but right now the APEX software doesn't have that capability. Okay, and I think the final question we'll take is, what would be the maximum allowed error percent to consider the true presence of an element? Very good question. So we look for the ability to distinguish the peak above background to make a conclusive determination of whether that element is present. And so when we report our error percentage, we report it with a statistical confidence level. Anything that's below 33% would be considered 1 sigma or 1 standard deviation likely to be present in the sample. So something as about lower than 33%. And just to recap, the optimum dead time for an EDAX octane detector, we would typically advise the 10 to 30% range, and with the Octane Elite, we're looking at the lower than 10% range. And I will take one more final question. This one is, how would it affect your energy channel calibration when you work at different accelerating voltages? And the good news on this one is that the calibration controls the x-axis energy of the spectrum. The calibration is actually done at 25 kV, but when we do this, we take 2 peaks. We take a high energy peak and a low energy peak, and we calibrate for each of those high and low energy peaks location on the x-axis, as well as any shift or stretch. So the single calibration collects and corrects for any range of kV. The lower aluminum energy peak that we calibrate for is at 1.486 keV, so even at the very lowest conditions, we see that it's calibrated. If you're working at the extremely low conditions, we also have an ICC shift correction that works for our carbon peak as low as carbon. So one calibration is used for all different accelerating voltages. Okay, and if you'd like to follow up with additional resources available from EDAX, please stay posted with our blog, some really interesting examples, an upcoming interesting one on applications from my colleague Jens, and also some movies out there, social media. Follow us on LinkedIn and Twitter. And please do register for upcoming webinars or check out the webinars that we've done in the past. We'd love to see you log on. And if you have any follow-up questions, feel free to contact us at info.edax@amatech.com. Thank you very much for attending today's webinar.